Hi everyone. Hope you've had a good day so far. So today I'm just going to give a bit of an overview of the geochemistry of the Mount Rawdon gold deposit in southeast Queensland. It's a really nice example of where a bunch of the conceptual geochemical patterns really work quite nicely. Firstly, I'd like to give an acknowledgement of country to the traditional custodians of the land that you're meeting on today, that I'm presenting from, and from the Mount Rawdon area, and paying my respects to elders past, present, and future, acknowledging the rich history that they have in all of those areas. So today, as I've mentioned, the focus will be on the hydrothermal geochemical patterns that we see around Mount Rawdon gold deposit. But firstly, I'll just give a quick intro to evolution and to the local geology before getting into the Pathfinder element geochemistry, which will be probably the main focus. Then talk a little bit about the alteration geochemical patterns and spatial patterns that we see. Some useful stuff in the spectral responses before some brief summary and insights. So evolution, most of you probably know who we are. We're a mid-tier Australian-focused gold company. We've been operating the Mount Rawdon assets since about 2012 now, though Mount Rawdon itself has been operating since 2001. And it's produced just over 2 million ounces of gold thus far, with just under 500,000 ounces of gold in the current resource. The resource is quite low grades, but we are getting towards the end of the mining history, with processing due to continue for another few years after that. A project that a number of you may have heard of, that we're kind of excited and proud to be involved in at Evolution, is the Mount Rawdon pumped hydro, which is looking at basically creating a really big battery for southeast Queensland, and so potentially a key project as part of the future energy infrastructure in Queensland. Hopefully that progresses as planned, and an exciting thing to be part of as a company. So to step into the local geology now, I'm not going to talk obviously too much about the regional, because we've zoomed straight into a pit and a nice splattergun, bit of a Jackson Pollock in leapfrog setup we've got going on here. So this is the local geology of the Mount Rawdon pit. You can see that this is draped on a DTM, and so you can probably see the pit around there. It's about 300-meter scale there. And so the geology we're looking at here is of a dominantly felsic to intermediate package of volcaniclastics, mainly breccias, but with some tuffs and some lavas, and then that's been intruded by dacitic to rhyolitic stocks pre-mineral. So a large volcaniclastic package that's mainly in the oranges and browns of slightly different compositions that you can pick out with the geochemistry and visually to varying degrees. Then there's a couple of prominent intrusions, being the eastern dacite through here, which does host a minor component of the mineralization. Also the western dacite, that only hosts a very small amount of mineralization. With this used to be a hill, now it's a hole. So the top of the deposit originally was in about this position up here, and then plunging down as a pipe of low-grade mineralization through the volcanics, the dacite stock and volcaniclastics towards the south-southwest. So the continuation of the deposit is underneath. So this volcanic complex sits within, it's surrounded on kind of three and a half sides, I guess you'd say, by the pre-mineral basement, being the Permo-Carboniferous sedimentary sequences. So it's almost completely surrounded down to more than half a kilometre below surface. So it looks very much like a diatreme or excavative volcanic environment. There's also some post-mineral to late mineral basalt andesite and also rhyolite to it. to trachytic dikes that you can see kind of crisscrossing through here. So just to introduce, I guess, a view that we're going to see a fair bit through this presentation of the deposit, just a simplified geology view there. So we're kind of looking towards the northeast to north, excuse me, and just showing here a couple of the prominent bodies. So we've got some post-mineral dikes that are generally these shallowly dipping things through here. The more felsic ones are in the pink and reddy colours, and then more andesitic one through there in green. They're post-mineral. The pre-mineral units we have here, that's the eastern dacite through there, and then the western dacite, and this other orangey mustardy body. And then the gold shells above 0.7 grams is shown in this grey. So you can see that that's forming a kind of a plunging, roughly pipe-shaped body from the top up here heading down towards the southwest. So just to touch briefly on the lithogeochemistry, this was quite relatively insightful in addition to the Pathfinder patterns that I'll spend most of the time talking about today. But we've got a calcalkaline, mainly moderate to high K calcalkaline sequence that ranges in composition from basalts through to rhyolite, but is dominantly dacitic is probably the most voluminous composition in there, most of the rhyolites being post-mineral. And you can actually break out using a simple plot of titanium versus niobium, so a compatible versus incompatible element that breaks out the units really quite nicely, and also allows more consistent differentiation of some of the volcaniclastic package that we see through here that because of its similar composition tends to look fairly similar, and so can be difficult to log consistently, but the geochemistry allows more consistent classification. One thing that was realised through this was actually a cryptic, more rhyolitic plug that was coming up through the deposit, actually forming a slightly lower grade zone that hadn't been recognised before we did this geochemistry, because it looked very, very similar to the eastern dacite and other units. Just touching briefly on the hydrothermal alteration itself. I do love rocks, but I'm not going to spend a whole lot talking about actual rocks today. But what we see in terms of the hydrothermal alteration is what's been documented is earlier propylitic, chlorate carbonate dominated assemblages, and earlier quote unquote phyllic, so quartz, sericite quartz plus or minus pyrite. But then it's been interpreted there's over printing stages of quite similar alteration assemblages, being varying from sericitic through to silica pyrite plus minus feldspar, some more chloritic alteration assemblages, and also starting to get some actinolite albite in zones increasing at depth. The post-mineral dikes generally show lower temperature inlets. So the mineralization itself tends to occur as kind of clots, irregular fracture-controlled zones, sometimes infilling and preferentially going into kind of matrix first classed within the pre-existing volcaniclastic breccias and little veinlets and things like that. So yeah, often associated locally with blobs of chloritic alteration, also actinolite albite. So we see dominantly pyrite, but you do get minor base metal sulfides, and as accessory minerals you see some sulfur salts, bismuth sulfide and sulfur salts, also pestle. So what I'm going to talk mainly through is actually the results of a geochem survey that was done about 10 years ago. It's a little bit scary to say. So this was actually not long after evolution had acquired the deposit, and we were looking to understand if there was other opportunities, particularly in the near mine environment and for extensions of tourism. So we wanted to, given the nature of the system, the fact that it's hosted, it's a relatively diffuse ore style and host rocks where you often see good zonation. We went ahead and took about 15,000 shortwave infrared measurements with an ASD to get the spectrally active mineralogy, and also took about 2,000 analyses that we had with this Bioforce Digest AIG-ALS, to complement about 800 existing chemical samples, but that were concentrated in a couple of different in 2 holes. And so this data set allowed us to build basically a 3D model of the hydrothermal architecture of the deposit and its immediate environs, and provided a really nice little case study that one key lesson out of this is around data distribution and how you decide what you're going to spend your money on to get an appropriate spread of information to tell a story and actually be useful. So here's an example here on the left. This was the data, the multi-element geochemical data that existed when we acquired Mount Rawdon, which was 2 deep drill holes where every second sample, I think, had been analysed by a Rolls-Royce complete characterisation package. For the same amount of money, we sampled about 17 different holes at 5 or so metre spacing down those holes, and we're able to build a 3D model of the deposit as opposed to just get a couple of holes. Don't give you spatial context. So data distribution is key, and you can change the amount of value you get out of spending the amount of money and spending how much thought you put into the So to get into the Pathfinder element geochem, we see some really nice, quite clear zonation patterns at Mount Rawdon, particularly in Pathfinder element metals that reflect both the epizonal environment in which the deposit's forming, probably in the upper couple of kilometres of the crust where we've got prominent temperature gradients, and also the relatively high permeability of the host rocks. So we can develop those gradients and have relatively kind of consistent fluid flow through those areas. As with most intrusion-related gold deposits that I think this is, there's a very strong relationship between gold and bismuth throughout the ore zone. And so the zonation that we see that we're going to talk to, likely reflects mainly the substitution of Pathfinder elements into pyrite as we see decreasing temperature, and also some other minerals, chlorite and carbonate, as we see possibly increasing pH or neutralization around the edges of the fluid plume. So we're seeing similar kind of zonation patterns overall to things that people like Scott Halley. This is just a summary, kind of looking from deep to shallow to marginal of the elements that we see through here that I'm about to step through. So just before we get into that, just to look at the association of gold with other elements. So this is a really nice way I find of splitting out data and seeing what's going with gold, what's not at the scale of the sample. So just breaking up into bins based on gold grade, and then looking at probability plots of those gold grade bins of the other elements. So you can see here there's quite nice associations to a point with things like silver and copper, but in particular bismuth and tellurium, and also sulfur. We're seeing some really clear relationships. Other elements that are commonly useful and here useful Pathfinder elements, things like antimony, arsenic, moly, lead, zinc, are really useful Pathfinder elements, but don't co-occur very much with gold. They form spatially medial to marginal patterns, zones around the gold zone. So let's have a look at some of those things in 3D with some leapfrogs. So we're seeing a similar view here to what we did in that initial view that I showed, looking approximately to the northwest. On these, usually the coloured blobs are essentially 3D contours or isosurfaces of different concentrations of the elements, and then the grey transparent you can see through there is the 0.7 grams gold contour or isosurface for the deposit. So as mentioned, there's a very strong relationship between bismuth and gold, and also tellurium and gold. So we do see some zonation through the deposit of tellurium. But this is just to show bismuth. So where we're going from the top of the ore body down through it, you can see there's a really nice correlation between the outer 5 ppm bismuth and then 10 ppm bismuth shares there with where you're seeing the to now look at some kind of more proximal and also deeper Pathfinder elements. As I mentioned, there's a strong relationship simply between gold and sulfur, but we do see increasing proportions of sulfur, which is primarily occurring in pyrite as we go to depth, and in some kind of non-directly mineralization related hanging zones up the edge of the western data. So you can see here on the contours of 1.5 and 2%. Sulfur as we're kind of increasing as we get down to depth within the deposit. So there have been deeper holes drilled down here where we saw very significant proportions of pyrite, but with relatively to show the relationships there with tellurium at 0.5 and 1 ppm. In the orangey colours, and then silver tends to be more concentrated, not economically significant values, but concentrated in the upper part of deposit, showing that zonation from deeper, likely hotter, to the upper cooler parts of the deposit. Interestingly, copper, we also see having a similar distribution to silver, looking now at the kind of more shallow to upper parts of the ore body. So we see copper, again, not particularly high values, but seeing that at 200, 400 ppm kind of thing in the upper parts of the ore body, similar to silver in blue over here on the right-hand side. In the middle is arsenic. The contour I'm showing there is above 150 ppm. So we're seeing that within the deposit, particularly in the upper parts, and also around the margins of the deposit. There's some zones over here that define what we thought might be another target that was tested at the time over there as well. Likely, if the deposit didn't stop there on top of that hill, if it was still intact, we probably would have seen increasing after concentrations sitting up above as well. So to look now at some of the elements that form nice peripheral zones, zinc, we don't get a lot of it through the ore body itself. Where that's concentrated tends to be right around the edges and extending out a couple of 100 meters around the margins of the deposit, as does manganese, forming a nice kind of halo shell around the deposit there. So both these minerals both these metals are sitting not so much in sulfides, but probably significant proportions of them in chlorite and also carbonate, which is something that you also commonly see in the classic porphyry system, where we're seeing neutralization halos going from sulfide to silica. Another nice way of displaying this and visualizing all these bits of zonation together is a technique that Greg Morrison has used a fair bit in the past, where basically you define the metal associations that you see throughout your data set. You can do that visually, correlation coefficients, PCAs, and then calculating Z scores for those, and then basically attributing a sample by the group that has the highest Z score. So that's most relatively enriched compared to the data set background. And you see some really quite nice patterns through here. So you can see that bismuth tellurium zone there, defining the deeper parts of the ore body, going up into the silver copper. Then we have the marginal zinc and arsenic, and then out to manganese. So it's just a nice way of being able to visualize things and use this deposits where you see more diffuse mineralization style. So to talk a little bit about the alteration geochemistry now, this is probably less useful than the Pathfinder element zonation in the case of Mount Rawdon as an exploration vector, but still quite useful. So what we can do here is plot our samples on the basis of molar sodium over aluminium and potassium over aluminium ratios to look at the cation chain mass balance changes associated with alteration. So most unaltered or weakly altered rocks will plot generally in this area and head up this way as they get more felsic. But we can plot patterns in that represent the loss or gain of potassium or sodium in these rocks, and generally like to head towards 1 mineral node, depending on what the dominant mineral in that alteration assemblage is, and the closer they move to a mineral node, the more intense the alteration is. And so the dominant pattern that we see at Mount Rawdon is out here towards muscovite. So the dominant, that's the kind of the dominant mass change in those cations. It doesn't mean that these rocks don't have cerussite in them. It just means that it's using potassium that's already to make that potassium. We also see a population up here, which is heading up towards potentially the fengite, and also ratios where there likely needs to be a bit of potassium feldspar in there as well to explain those potassium issues. So if we look at that and then do a split probability plot, which is another nice way of representing the different associations you might see between elements and alteration zones, we see that there's a strong bias towards higher gold values within this population that's got the high potassium. So if we have a look at that spatially, I won't look at this too much. It's always hard kind of showing things in 3D, but just trust me. So here's a simplified diagram. This is actually a real cross-section. It's not schematic. It's where I've actually cut through this and then done an insert straight on it. So what we see is that there's a couple of relatively flat shallowly dipping zones that parallel and go through the middle of the ore body, where we see stronger cerussitic alteration at depth and then going into that increasing potassium over aluminium ratios and then into a closer to surface, which is really interesting and mimics an increase in the fengitic mica component. And possibly reflects an increase in pH as we're going through here. So these features here are relatively distinct in the geochemistry, but if you look at them, the alteration assemblage looks very similar to the rocks. That's quite apparent in the geochemistry. These are also some of the key gold higher grade gold zones through the ore body as well. So it looks like what we're doing here is actually mapping some of the more important fluid flow controlling structures. One of the other cool things we can do is have a look at the various aspects of the composition and the temperature of formation of the sericite throughout the deposit. It's a nearly ubiquitous mineral occurring in most rocks. There's a couple of things we can do. We can look at the wavelength of the aluminium hydroxyl absorption feature in the squiggly line spectrum, where we see more fengitic, longer wavelength white mica is usually associated with formation in more near neutral and closer to feldspar stable conditions. We tend to see associated with more acidic, but still relatively weakly acidic conditions. We'll see more muscovitic and even to pergonitic and shorter wavelengths of that absorption feature. We can also use this to look at a ratio of a couple of different features that gives us an indication of the degree of crystallinity of the spectral maturity of the illite to white mica. That gives us an approximate estimate of the temperature formation. So if we have a look at what those things look like spatially, as the data there, and then again a cross section where I've just picked out a couple of contours there. And so if we look at the sericite crystallinity ratio, you can see that we're seeing a reasonably homogeneous pattern there where we're going from higher sericite crystallinity, which is reflecting higher temperatures. That's decreasing slowly as we go up through the deposit, but more so as we go out of the deposit. And so at about 1.75 sericite crystallinity value, which is just ALOH absorption depth over 200 absorption depth, we have a halo that sits at 200 meters. So and then the other thing we can look at is the sericite composition. And so what we tend to see in the data here, we do have a zone of more fengitic white mica sitting over towards the west and southwest, and then a plume of slightly more fengitic white mica. We're not talking particularly fengitic here, it's 2207, so just a little bit of Chermak substitution above muscovite. But that seems to persist through the ore body, where we have some shorter wavelengths and likely more aluminium, which possibly slightly more acidic formed assemblages around that. Interestingly, as I mentioned, you can see here you're getting an increase in the red as we get up to the top of the ore body. That's likely reflecting those more fengitic compositions. So overall, from the mineral zonation, I think it defines some really nice patterns. You can see when you're outside coming inside to the ore body, and also the relative level of that, which is of course an important thing to consider when you're exploring as well. You don't want to find an ore body that's pretty much all gone. So being able to tell the relative position you are in the system is sort of quite useful. So it's a summary there just of the zonation patterns I described before. And so where you're seeing that the sericite crystallinity gradient just outside. So overall, I'd suggest based on the patterns plus combined with the previous work that's been done at the deposit, an epizonal intrusion related gold deposit, it looks like there's evidence of potential boiling to be able to get the mixed fluid inclusions, and also that change in the alteration assemblages and the geochemistry as you go into the upper parts of the ore body as well. So I guess just to refresh that as well, I mean, I think this is a really good example of a deposit where we've got some great zonation patterns. They don't always look this good. I think the permeability architecture of the environment of formation, and also the presence of gradients, particularly temperature, but also pH and pH are things that have a significant control on how good the geochemical zonation, how clear it can be around a given deposit. But this is a kind of a mixed case study. And I guess to me it goes to the value that you really should be trying to derive as much as possible from in your what are now just kind of best practice data sets to collect, I think, before turning to new technologies like mineral chemistry and things like that are more difficult to apply and interpret. That's me. Thanks very much.
We've probably got time for one or two quick questions if there is any, or we can
speak up if you do have any questions. Those green lights are where the microphones are. So Ned, can you hear us, Ned?
Yeah, I can hear you.
Any questions? Oh, you bamboozled them. Brilliant.
I got one. Can you elaborate, like that look like going up? Is that a structure that that your hydrothermal alteration is being defined? So what is that?
Yeah, so there as I kind of mentioned around the alteration geochemistry, I think that's mapping a couple of structures through there, but generally there's not a clear single direct structural control on that. There's probably a number of faults that have contributed to that kind of tongue going up through that way. But interestingly, it does cross through, like it's mainly in relatively permeable breccias and things like that, but it does cross through into a dacite stock, which is obviously going to be much more rigid. Interestingly, where you see a flexure in the contract and a fault on one of these others, where those likely fluid feeder structures come through the contact as well. So it's a combination of that inherent permeability in these rocks, and also some fluid flow control faults as well.
Is there one more question? Tom? Yeah.
G'day, Ned. Thanks for that.
No worries.
My question's related to Henry's, really, but has anything been rotated sort of post-emplacement there, or do you think all of that fluid was just scooting up sideways at Grace?
Yeah, I don't think there's a lot of evidence for things having been tilted a whole lot. I mean, it's hard to like there is a tilting from in the sequences in the deposit that's dipping not as steeply but close to the direction of it. So if you were to rotate that, the plume would actually be shallower. But it's hard to say given the environment. We're in probably a diatreme / an excavative vent where you can get tilting and things like that as you get slumping. So it's hard to be specific on.
All right. I think that's it, Ned. Thank you.
No worries. Thanks everyone. Enjoy the rest of the day.